When I say, what if reality is not loading properly, I'm not talking about a glitch in a computer simulation. I'm talking about something more concrete and stranger. I mean the way the universe behaves on the largest scales, the way space stretches, the way gravity works, the way most of the mass energy in the universe is invisible and only shows up its effects. From the point of view of human intuition, reality does not seem to be loading in the way we would expect from the matter we can see and the physics we first learned. And yet, the data are real. The question is whether our mental picture of reality is what needs to be fixed. I want to start with what we know best, gravity as described by general relativity. In that theory, gravity is not a force pulling things together through empty space. Instead, mass and energy tell spacetime how to curve, and curved spacetime tells matter how to move. I picture it as a rule book for how rulers and clocks behave. Put mass and energy somewhere, and the rules for measuring distance and time change around it. Planets orbit stars because they follow the straightest possible paths in a curved spacetime. Light bends around galaxies for the same reason. This description has passed every test in the solar system and in many astrophysical systems. Mercury's orbit, the bending of starlight by the sun, the time delay of signals passing near massive bodies, the slowing of clocks in GPS satellites, gravitational waves from colliding black holes and neutron stars. All of these match general relativity with high precision. If gravity is so well tested, where does the feeling of reality not loading properly come from? It shows up when we look at the universe as a whole, at galaxies, at clusters of galaxies, at the expansion of space itself. When we plug what we see into Einstein's equations, using only normal matter that interacts with light, the equations do not balance. The motions are wrong. The expansion is wrong. The large-scale structure is wrong. It is as if the universe is running on hardware we do not see. Let me walk through dark matter first. Dark matter is the name we give to whatever is causing extra gravity without emitting or absorbing light. We discovered it not by seeing it, but by noticing that visible matter is not enough to explain what galaxies and clusters are doing. In the 1930s, Fritz Zwicky studied galaxies in the Coma cluster. He measured their speeds and used the virial theorem, a tool from mechanics, to estimate how much mass the cluster must have to hold itself together. The answer was much larger than the mass of all the visible galaxies. He called the missing part Dunkel Materie, dark matter. At the time, the evidence was rough, and many people were skeptical. Decades later, Vera Rubin and collaborators measured rotation curves of spiral galaxies. If most of the mass in a galaxy was in the bright central region, then stars far from the center should orbit more slowly, like planets in the outer solar system. Instead, the rotation curves flattened. Stars and gas at large radii moved almost as fast as those near the center. That meant the mass did not drop off with distance the way the light did. There had to be a large halo of unseen mass extending beyond the visible disk. This pattern appeared again and again in many galaxies. Since then, independent lines of evidence have piled up. We see dark matter in gravitational lensing, where the path of light from background galaxies is deflected by the mass of a foreground cluster. The amount of bending is often much larger than what visible matter alone would cause. The Bullet cluster is a famous case. Two clusters of galaxies collided. The hot gas, which we can see in X-rays, slowed down and interacted. The galaxies, mostly empty space, passed through. But when we map the mass using gravitational lensing, most of the mass is not where the hot gas is. It is centered near the galaxies, as if an invisible component passed through the collision without interacting much. That is exactly what we expect if most of the mass is in a collisionless dark matter halo. We also see dark matter in the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature fluctuations in that radiation encode information about how matter and radiation were distributed about 380,000 years after the Big Bang. The pattern of those fluctuations and the acoustic peaks in their power spectrum match a universe where about 5% of the energy density is normal baryonic matter, about 25% is dark matter, and the rest is something else we will get to soon. Without dark matter, the relative heights and positions of those peaks would be different. The way galaxies and clusters grow from those initial fluctuations over billions of years also fits a picture where dark matter provides most of the gravitational scaffolding. So, from many angles, the equations tell us the same thing. There is extra mass that does not interact with light. We do not know what it is made of. It could be a new kind of particle, or a family of particles. It could be something more exotic. But it is not just a patch on one observation. It is a consistent ingredient in a model that matches a wide range of data. That is why most cosmologists take dark matter seriously. It is not that reality is glitching. It is that our original expectation that visible matter is all that matters was wrong. Now let me turn to dark energy. If dark matter makes gravity stronger, dark energy acts in a way that makes the expansion of the universe speed up. Here the story begins with the discovery that space itself is expanding. In the 1920s, Edwin Hubble and others measured the redshifts of galaxies. Redshift is the stretching of light to longer wavelengths as objects move away from us. They found that more distant galaxies had larger redshifts. The relationship was roughly linear, velocity proportional to distance. The simplest explanation was that space between galaxies is expanding. Every galaxy sees others receding, with speed increasing with distance. General relativity allows solutions where the universe expands or contracts. A static universe is unstable unless you fine-tune a term called the cosmological constant. For a long time, cosmologists thought the expansion might be slowing down due to gravity. The question was whether the universe had enough matter to eventually halt the expansion and recollapse, or too little matter, so that expansion would go on forever, just slowing. In the late 1990s, two teams used Type Ia supernovae as standard candles to measure distances to faraway galaxies. These supernovae have relatively uniform intrinsic brightness, so by comparing their apparent brightness to what we expect, we can estimate their distance. The teams compared those distances to redshifts and found something surprising. Distant supernovae were dimmer than expected in a decelerating universe. They were farther away than they should be if expansion had been slowing. The data fit a model where the expansion of the universe has been speeding up over the last few billion years. To explain this, cosmologists revived the cosmological constant. In Einstein's equations, it acts like a uniform energy density filling space with negative pressure. In general relativity, not only energy density, but also pressure gravitates. A component with strongly negative pressure can cause the expansion to accelerate. We call the unknown cause of this acceleration dark energy. The simplest model is that dark energy is just a constant vacuum energy. Quantum field theory suggests that even empty space has some zero-point energy. But naive calculations of that energy density give values far, far larger than what we infer from cosmology. That mismatch is one of the biggest unsolved problems in theoretical physics. We know dark energy is there not only from supernovae. The cosmic microwave background, combined with measurements of large-scale structure, tells us the geometry of the universe is very close to flat. If you sum up the contributions from normal matter and dark matter, you get only about 30% of the critical density needed for flatness. The rest must come from something else, consistent with dark energy. Baryon acoustic oscillations, which are imprints of sound waves in the early universe on the distribution of galaxies today, also support the same expansion history. These different probes converge on a model called lambda CDM, lambda for the cosmological constant, CDM for cold dark matter. It is a simple model with a small number of parameters, and it fits a wide range of observations remarkably well. Yet, from a human point of view, this model feels like reality is not loading properly. About 5% of the universe is made of stuff we understand fairly well: atoms, radiation, neutrinos. About 25% is dark matter, which we infer but have not directly detected in the lab. About 70% is dark energy, whose physical nature is unknown. The part we can see and touch is a small correction on top of two dominant components that we perceive only through their gravitational effects. It is tempting to say the universe is hiding its main ingredients. But in science, we do not treat this as a glitch. We treat it as a measurement telling us that our earlier picture was incomplete. How do we know we are not just misinterpreting gravity? Could it be that there is no dark matter or dark energy, and instead general relativity breaks down on large scales? This is a reasonable question, and people have tried to answer it. There are modified gravity theories, like MOND, modified Newtonian dynamics, and its relativistic extensions, that change the laws of gravity at low accelerations to explain galaxy rotation curves without dark matter. These models can fit some galactic data, but they struggle to match the full range of observations, especially the cosmic microwave background and large-scale structure. Similarly, there are models that try to explain cosmic acceleration by modifying gravity on cosmological scales instead of adding dark energy. Some of these are constrained strongly by gravitational wave observations, which show that gravitational waves and light travel at essentially the same speed over cosmological distances. Many modified gravity models predicted differences that are now ruled out. So far, general relativity plus dark matter plus dark energy is the simplest framework that matches all the data we have. That does not mean it is the final word. It means that any alternative must reproduce the same successes. It must explain galaxy dynamics, cluster lensing, the bullet cluster, the cosmic microwave background power spectrum, baryon acoustic oscillation, supernova distances, structure growth, and more all at once. That is a high bar. Now I want to connect this back to the idea of loading reality. In a computer game, if textures load slowly or physics behaves oddly, we blame the engine. In cosmology, when the universe behaves in a way that feels counterintuitive, we check the data, we refine the models, and we try to see whether the underlying theory needs to be changed or just extended. Dark matter and dark energy are extensions. They keep the core of general relativity, but add new components to the energy-matter content of the universe. From the equations' point of view, this is not a hack. The equations do not care whether the energy density comes from atoms, photons, or some new field. They just respond to the total stress energy. However, our intuition about space and time does get stretched. One of the strangest aspects of dark energy is that as the universe expands, the total amount of dark energy increases if it is truly a constant energy density per unit volume. More space means more vacuum energy. That sounds like energy appearing from nowhere. But in general relativity, energy conservation is more subtle on cosmological scales. There is no global energy conservation law in an expanding universe in the same simple sense as in Newtonian physics. Locally, the laws of physics still conserve energy momentum. Globally, the changing geometry allows the total bookkeeping of energy to behave differently. This is an area where our everyday concepts do not map perfectly onto the mathematics. Dark matter also challenges our sense of completeness. In particle physics, we have the Standard Model, which describes known particles and forces except gravity with great accuracy. But the Standard Model does not contain a good dark matter candidate that matches cosmological needs and experimental bounds. So we suspect new physics beyond the Standard Model. Many experiments search for dark matter particles. Direct detection experiments look for rare collisions between dark matter and atomic nuclei deep underground. Indirect searches look for signals from dark matter annihilation or decay in space. Colliders like the Large Hadron Collider search for missing energy signatures that could indicate dark matter production. So far, no conclusive detection has been made. That non-detection already tells us that if dark matter is a particle, its interactions with normal matter must be very weak, or its mass must lie outside certain ranges. The parameter space is shrinking, but it is still large. On cosmological scales, dark matter behaves as if it is cold. That means it was moving slowly compared to the speed of light when structures started to form. Cold dark matter clumps on small scales, allowing galaxies and clusters to grow from tiny initial fluctuations. If dark matter were hot, like very fast-moving neutrinos, it would smooth out small-scale fluctuations and delay structure formation. Observations of the distribution of galaxies and the Lyman alpha forest in quasar spectra support a cold or at most warm dark matter scenario. Again, this is not a glitch. It is a constraint. Now let me talk about cosmic expansion itself, because this is where the fate of the universe comes in. In the Standard Model, the universe started in a hot, dense state about 13.8 billion years ago and has been expanding ever since. Early on, radiation and matter dominated the energy density. Gravity slowed the expansion. As the universe expanded, matter and radiation diluted. Radiation energy density drops faster than matter because photon energies are also redshifted. A constant dark energy component, by contrast, does not dilute. So as time goes on, dark energy becomes more important relative to matter and radiation. Observations suggest that a few billion years ago, the densities crossed a threshold where dark energy began to dominate. From that point, the expansion started to accelerate. If dark energy is truly a cosmological constant, then in the far future, the universe will approach a state of exponential expansion. Galaxies not gravitationally bound to us will recede faster and faster. Eventually, distant galaxies will move beyond our cosmic horizon. Their light will never reach us. The observable universe will shrink to a region containing only our local group of galaxies, which will have merged into a single massive galaxy. Star formation will slow as gas is used up. Stars will burn out. Over trillions of years, the universe will become darker and colder. Black holes will dominate, then slowly evaporate via Hawking radiation over enormous timescales. Matter itself may decay if protons are unstable. This is the heat death or big freeze scenario. It is not dramatic in the way of a big crunch or a big rip. It is a quiet, long decline into a thin, cold, nearly featureless spacetime. There are other possibilities if dark energy is not constant. If its energy density grows with time and its equation of state parameter W is less than -1, we could get a big rip, where the expansion becomes so rapid that it eventually tears apart galaxies, stars, planets, and even atoms. Current data are consistent with W very close to -1 and do not demand such extreme behavior, but they do not yet exclude all dynamic models. If dark energy decays or changes sign, it could slow the expansion or even reverse it, leading to a big crunch. Again, there is no strong evidence for this in current data, but our constraints have limits. We are fitting a cosmic history of nearly 14 billion years with observations made from one point in space and time. This brings me to a subtle point about how we know what we know. We cannot run controlled experiments on the universe as a whole. We cannot reset initial conditions. Instead, we observe, we model, and we test consistency. We compare independent measurements that probe different aspects of the same underlying physics. For example, the cosmic microwave background tells us about the early universe. Galaxy surveys tell us about the later universe. Supernovae and baryon acoustic oscillations trace the expansion history. Gravitational lensing maps the mass distribution. If one model can match all of these, that model gains credibility. If tensions appear, they may point to new physics or to unrecognized systematics. Right now, there are some tensions. One notable one is the Hubble tension. Different methods of measuring the current expansion rate, h0, give slightly different values. Local measurements using Cepheid variables in Type 1a supernova tend to give a higher h0 than the value inferred from the cosmic microwave background under the lambda CDM model. The discrepancy is at a level that is hard to ignore, but not yet decisive enough to declare a discovery of new physics. It could be due to unknown systematics in one or more methods, or it could be a hint that our model of the late-time universe is incomplete. If it is the latter, it might tie into dark energy, dark matter, or modifications of gravity. This is an active area of research. So is reality not loading properly, or are we just still downloading the full theory? I think the honest answer is that our current model is both impressively successful and clearly incomplete. It explains a huge amount of data with a small set of parameters. It gives us a coherent story of cosmic history, from a nearly uniform early plasma to the rich web of galaxies we see now. It predicts phenomena like the detailed pattern of the cosmic microwave background that were later confirmed. At the same time, it leaves the main ingredients, dark matter and dark energy, without a firm microphysical explanation. It relies on general relativity, which we know is not a quantum theory of gravity. It faces conceptual issues like the cosmological constant problem and the nature of the initial conditions of the universe. From a scientific point of view, this is not a failure. It is a roadmap. Each gap in understanding is a direction to push. Dark matter motivates new particle physics, new astrophysical observations, and new gravitational tests. Dark energy motivates better surveys of supernova, galaxies, and gravitational lensing, as well as theoretical work on quantum fields in curved spacetime. The early universe motivates studies of inflation or alternative scenarios, and searches for primordial gravitational waves. The large-scale structure motivates increasingly precise maps of how matter clusters over time. When we ask whether reality is loading properly, we are really asking whether our theoretical framework is keeping up with the data. So far, the data are ahead. They show us a universe dominated by components we do not yet fully understand. They show us that space-time is dynamic, that geometry and energy are linked, that gravity shapes everything from the orbit of a satellite to the fate of all galaxies. They show us that human intuition, built in a small corner of a small planet, is not a reliable guide to cosmic behavior. We have to trust the measurements and the mathematics, and then work to build intuition that fits them. I will end with one open question that sits at the heart of this topic. We model dark energy as a cosmological constant because it is the simplest option that fits the data. But we do not know if it is truly constant, or if it is a field that evolves slowly with time, or if it is a sign that general relativity itself needs modification on the largest scales. The next generations of surveys and experiments are designed to measure the properties of dark energy more precisely. They will map the expansion history and the growth of structure with higher accuracy. They may show tiny deviations from a pure cosmological constant, or they may confirm it even more strongly. Until we know which way nature has chosen, our picture of the ultimate fate of the universe and our sense of whether reality is complete will remain provisional.